Okay, so welcome to Fluid Mechanics. And this first lecture, I want to announce that there's a lot of information that's going to be posted on Blackboard, the Blackboard site. How many of you have already seen the Blackboard site? All right, excellent. Almost everyone. That's very good. Hi, take a seat. That's great. So I'm going to be posting some videos, some extra material, and so on there for you. And I also have the intention of creating an iTunes course. So what is this course for? So I thought about what really we want from a course like this. It's your introductory course on fluid mechanics for mostly what you are, mechanical engineers. And I think one of the things that I would like for you to take away from this course is a sense of the importance of fluid mechanics in engineering. As engineers, you will encounter fluid mechanics in many, many applications. Even if you're a computer engineer or a civil engineer, you know, in other fields, you will encounter fluid mechanics. A computer engineer, computer architecture engineer may have to figure out the flow of air around the chip to see if it's going to be cooled appropriately, for example. A civil engineer may have to calculate the flow around a bridge structure to determine whether the wind may cause certain stresses that it needs to account for, and so on. So the importance of fluid mechanics in the engineering world. And also, I want to make sure that you develop a certain intuition and understanding of physical principles. With those goals in mind, I have thought about the course in detail so that we can really bring this out for you, okay, and try to not let the fact that there's a lot of theory put you off from the beautiful insights that studying fluid mechanics can bring. Just to give you an idea, this fluid mechanics is a very old subject. It's you know, even we can think all the way back to Leonardo da Vinci, but Isaac Newton for sure did a lot of study of fluid mechanics and laid down some of the theoretical foundations. So if you think about that, 300 years of humans like you thinking about problems and laying down the theory, there's a lot of mathematical explanations that have been brought forward to accompany the physics that we see. But in an introductory fluid mechanics, my goal is going to be to try to give you just enough of that for you to have the proficiency you need as engineers to go to your next courses, but with an emphasis on physical intuition. So what do we need to do first? We need to agree on what is a fluid. But what is a fluid in engineering terms? Okay, that's going to be our first goal today. So what causes splashing, for example? The splashing of milk as an object falls. There's a lot of interplay there of various physical properties of the fluid, surface tension, the viscosity of the fluid, the depth of the pool of liquid. All of this determines the pattern of the splashing. Now, there was a very famous professor in MIT called Edgerton who was able to capture with a high-speed camera that effect. And we want to try to understand in engineering terms. What causes a jet of fluid to pinch off like this? Well, there's a surface tension there that causes, right, the pinching off because there's a high pressure in the thinner areas, and that high pressure causes the fluid to kind of move away from the thinner areas once an instability sets in. What causes the dust devils? Dust devils are the same as tornadoes, but they occur on a small scale. They're caused by a column of air that moves vertically upwards due to the sun's heating. And because of the rotation of the Earth, you get this swirling fro that captures the dust. Look at that. I have this one twice because it's so amazing. The dust devil here. I don't know if it's repeating now. It is absolutely amazing. Here it is again. Just watch this one for a moment and imagine the physics that's behind that. What an incredible thing to look at and try to understand in engineering terms, the physics of such a phenomenon. Of course, tornadoes and the flows at the global scale, we would like to understand the physics behind that, perhaps express that in mathematics. Bubbles. Bubbles are created due to surface tension, which makes a film of liquid behave like an elastic membrane. Look at that marvelous display of nature there, the forces of surface tension. Look at this guy. This is the basilisk lizard. It's about 20 grams in weight. These creatures are able to run on water to flee from predators. They create a cavity under its feet, notice, and then it's able to run on water due to exchange of momentum. We want to understand that momentum. How can we use it to create some energy? Look at that. Balloons which are extended as they are filled with water and become punctured, immediately lose all tension, releasing the water and exploding dramatically. Look at this other bubble bursting. In this video, notice that there's two little satellite bubbles that survive the encounter with the ball bearing. Now, this video here shows you the phenomenon of cavitation. Lord Rayleigh was consulted by the Royal Navy in World War II to explain the erosion of propellers in ships, and he was able to pin down this phenomenon, cavitation. The origin of the damage is in the collapse of tiny little bubbles that are created because the water reduces its pressure to a point where it automatically vaporizes into miniature bubbles. The tears of wine. You guys are perhaps too young to have observed with much detail the tears of wine. This is fascinating. You can watch it for a long time. What are the physical explanations of the tears of wine? There's a combination of capillary effects. The surface tension is the difference of surface tension between alcohol and water. The alcohol evaporates quicker, and this is associated with an increase on the capillarity effects, draws the liquid to fall down by its own weight. We were going to aim to explain these phenomena in this course. The whole process is called the Marangoni effect, and later on in the course, I promise you we will come back to some of these and explain them and understand them in terms of the physics that create these wonderful effects. And the last one that I have is going to be also quite fascinating. This is called the K effect, caused when a shear thinning fluid hits it falls and hits a thin layer of the same fluid, in this case, shampoo. You can do this experiment at home with a bottle of shampoo and say a Pyrex kitchen utensil, and you can see this effect caused when a shear thinning fluid, and we will explain that later on, hits a surface and streamers eject from the fluid. You will see at any point those there, the streamers which eject from the fluid in a dramatic fashion. They shoot away. And there are a variety of materials that exhibit this type of behavior, and we're going to try to explain those in this course in engineering terms so that you can bring this intuition to your future exercise as engineers. Okay, so for your information, there's a small document that I will put on Blackboard that has all the credits of where I obtained all of these movies and a very brief explanation of the phenomenon as I've just related to you, so that you can see it in your own time. I will also put that video online so that you can watch it again if you're interested. So, splashing, jet breakup, dust devils, bubbles. How can a lizard walk on water? A water balloon explodes. Cavitation, the tears of wine, and the shooting jets of shampoo. All of those things we're going to try to explain in this course. But we go back to our question. What is a fluid? But in engineering terms. So we could perhaps want to think about a fluid in terms of some casual observation. So casually, you may see and think that a solid is somehow hard, a fluid soft, it deforms easily, but that is not really satisfactory from the point of view of an engineer. It's a bit too qualitative, isn't it? So maybe we want to look at the molecular structure. And if we look at the molecular structure, we will say, okay, well, a solid has densely packed molecules. That seems reasonable. A fluid, well, a fluid will have molecules which are spaced further apart. And that is more scientific, if you will. But is that enough? Well, if you think about in the realm of fluids, there's gases and there's liquids. And certainly gases, your observation and your knowledge of chemistry will tell you that gases will have their molecules much further apart than liquids. And so this is a qualitative explanation that is not completely satisfactory because we can't really distinguish solid, fluid, gas, liquid. So it's not completely, it's really not enough. It's a qualitative difference. So what is an engineering distinction of a fluid? Think about it for a little bit. These casual observations that I've presented to you don't seem to be enough, do they? What characterizes a fluid? Anybody want to throw a word out? It flows. Exactly. It flows. What is flow? What does it mean to flow? It's moving. How is it moving? And how long is it moving? Continuously moving, right? It doesn't stop unless you put something in between and stop it, right? It continuously deforms. It continuously deforms in response to a particular form of force, a tangential force, because if you imagine the water inside the balloon only has a sort of normal force, right, to all the surfaces, that's a pressure. But any tangential force will cause it to flow continuously. And that is really our engineering distinction. So, in engineering terms, a fluid deforms continuously when acted on by what we call a shearing stress. A shearing stress is what we need to explain next. A shearing stress is a tangential force. Stress is force divided by area. So we use tau for stress, and it's force divided by area. But shearing stress, if you look at this picture, we have tensional stress, compressional stress, and tangential or shear stress. So shear stress is the tangential force divided by area. When shear is applied to a solid, it simply reaches a position of equilibrium. It deforms, and we can measure how much, and the properties of this solid will determine how much it deforms, but it will reach a position of equilibrium. A fluid, well, flows. right? It continuously deforms. And that is really the distinction in engineering terms. Now, what resistance the fluid exerts to the shearing is determined by a property of the fluid called viscosity. So, viscosity. Now, this is a problem that was considered by Sir Isaac Newton way back when. And he considered theoretical the situation of, say, two parallel plates. Say this is, I'm looking at a cross section of two parallel plates, okay, where there is fluid in between. Let's say that the distance between these two parallel plates is h. Well, no, I think I've called it y here in my. So, based on observation, Newton observed the following, that the force, if I pull this plate at the top with a velocity u, capital U, and this one here is stationary, this fluid in between the two plates everywhere, the force is equal to viscosity of the fluid times the area multiplied by the velocity and divided by the distance between the two plates. So capital U is the velocity of the top plate, y is the perpendicular distance between the plates, and mu is the coefficient of viscous resistance. Now, in modern engineering, we use, instead of the force, we use the shear, and so we use in terms of the shear, tau, which is equal to force divided by area. We introduce the shear to write, and again, also we take a limit when the plates, basically, we imagine that these plates really are two very thin layers of fluid, and we want to look at two layers of fluid very close to each other. So we take the limit and we write, instead of u, we write, y, we write dy, and instead of u, we write just u being small u, the velocity of any layer of fluid, and we write the following relationship, which is an experimental observation. The shear stress tau is equal to mu times du dy. This is for the case that I've illustrated in this slide, which is the case of 2D, two-dimensional planar flow. So what is du dy represents what we call the strain, the shear strain, and the shear stress is tau. And we're saying in this case that there is a linear relationship between the two in this experimental observation. Now, if you're not completely satisfied by this more physical explanation and you're more mathematically inclined perhaps, there is more detailed derivation of this exact equation here that I have in the box. Before I have done the whole derivation in class and found that many of you were really not that interested to know all of those gory details. And so what I've done is I've made a little movie of that and I placed it, I'm going to place it for you on, I think I put it already there last night, on Blackboard for you to look at the derivation if you're so inclined, if you're more mathematically inclined. And I will do that with several other derivations that we will see that appear during the rest of the course. And that is just to satisfy those of you who really want to understand where every equation comes from. There's a few people like that, and there's a few others that actually are content with a physical explanation that makes sense. Okay? So you are invited to see the theory video, I call it the supplementary theory videos that I'm going to place for some of the lectures. So the property of viscosity makes two fluids behave very differently when they are in motion. That is what it boils down to. All fluids deform continuously, but they behave differently depending on the value of their viscosity. The two fluids shown in the video there in the left are perhaps water and glycerin. They have very similar density. The density really is does not matter in this business of the motion. What is different is their viscosity. In the video on the right that I need to start, I believe you will see 4 different liquids of very different density. And can I do that again? There. And you can see that their behavior as a jet falls into another fluid is very, very different. The property of the fluid that determines that is the viscosity. Okay, so a couple of more things about viscosity. For a given fluid, viscosity depends very strongly on the temperature. It doesn't depend very much on pressure, but it depends very much on temperature. Now, in truth, it is not always a constant value like we've placed in the equation we just had before, where we wrote tau. We wrote before tau is equal to mu du dy. And here we assumed, of course, that the viscosity was a constant. But that's not always the case. Okay. And in fact, the relationship between stress and strain is not always linear. Most of the fluids that we encounter do have a linear relationship between stress and strain. Those are the fluids we call Newtonian fluids. Those are the ones we encounter the most in engineering. Certainly water is Newtonian, air is Newtonian, and so obviously on planet Earth, water and air are the most abundant fluids, and so we deal with those a lot in engineering, and they are Newtonian. But if you're involved in processing engineering and you have to design some equipment for toothpaste or ketchup, then you will find that the relationship between stress and strain is not linear for those fluids. So what is the definition of a Newtonian fluid? This is a fluid for which the shearing stress tau varies linearly with the rate of shearing strain. du dy. So if we were to draw a plot of tau as a function of du dy, we would have for different fluids, perhaps different slopes, but the plot will always be a linear relationship. So for example, you might have, oh, that's not the one I want. Let's see that one. Let me see, red. You might have a line like this, say for air. You might have a more viscous material here. This could be perhaps water, or this could be, say, oil. But the relationship we see in that plot is a line, and the slope of that line is mu. It's a linear relationship between stress, the shearing stress, and the rate of shearing strain. In the case of the non-Newtonian fluid, things can be different. So in this case, this is a fluid for which the shearing stress is not linearly related to shearing strain. So if we were to draw in that case a plot again of stress as a function of strain, we might see some different things. We could see perhaps a line that indicates an increasing slope like this. And the increasing slope means that, well, basically the slope is increasing, so the viscosity is increasing, right? And we call something that behaves in this way a shear thickening fluid. It gets thick as we press it. Oh, not press it, really. Shear it. That's the correct word. Shear thickening. Okay. So that means that mu increases. Now we could also have a behavior where the slope on this plot decreases like that, and we call that a shear thinning fluid, where mu decreases. Have you noticed when you get a pot of yogurt and you put the spoon in there, it kind of sit there without moving, but if you stir it really quickly, it becomes liquidy. Have you noticed that? Have you? That's because of thinning, shear thinning. There are many products, food products or cosmetic products or things like that, that have that property. That as you, I think mayonnaise as well. If you stir it real fast, it will flow more easy. But if you don't move it, it doesn't really flow. It just sits there, right? It's quite viscous. Blood is like that as well, but the effect is quite more mild. And so really in many approximations we can just say it behaves like a Newtonian fluid, and that's also useful. It depends on the magnitude of the shear stresses that are involved. And so in many studies of blood flow, people will assume that it's a Newtonian fluid, but it really isn't. So you need to bear in mind that perhaps in some situations the non-Newtonian behavior becomes important. As engineers, you always have to juggle the relationship between taking into account all of the physical effects and perhaps solving a problem with simplicity so that you can get an engineering answer, so you can make some approximations. But there are many fluids that will behave in this nonlinear way. There are a couple of definitions that we need to introduce here at this point. The no-slip condition. This is an experimentally observed fact shown here in this movie. We have water in some sort of tank flowing there, and a needle is introduced with some dye. And the dye that is placed very close to the wall, as you can see, sticks there. But as soon as it's removed from the wall, as soon as it's further away from the wall, it flows with the rest of it, with the rest of the water in the wind tunnel. Again, you see, the dye very close to the wall is not sticking. Really, the water that is really close to the wall is sticking. Viscosity has that effect, that the fluid wants to stick to the wall. And this is what we call the no-slip condition. It's an experimentally observed fact. That a fluid moves with the solid boundaries. So if the solid boundary is stationary, the first tiny layer of fluid next to it is going to be stationary as well, infinitesimally small layer. And the velocity of the fluid will slowly go up from that value of 0 at the wall to the value of free stream. Okay, the dimensions of viscosity. Recall, this is the equation that we introduced for viscosity in the case of Newtonian fluids. Remember, this is particular for the case of Newtonian fluids, where there is a linear relationship between the shearing stress and the rate of shearing strain. So what are the dimensions of tau? Well, we said tau is equal to force divided by area. So force is, in just dimensions, let's just use force and length squared for area, without introducing units, just dimensions. How many of you have watched the movie, this very quaint movie, Introduction to Fluid Mechanics, that I put on Blackboard and I invite you to watch? Some of you have? Excellent. Thank you very much for taking the time to watch that movie before the first class. I really appreciate that, because that makes it easier for me to stress some of these points, like dimensions. Professor Rouse introduced the fundamental dimensions, he said, of fluid mechanics are force, length, and time. Sorry, force or mass, length, and time. All mechanics have these fundamental dimensions. So in this case, for shear stress, we have force divided by area, or force divided by length squared. du dy, well, let's see, u has dimensions of velocity, right? So velocity is distance divided by time, so length divided by time. And y is just length, so this is 1 over length because it's in the denominator here. And so we get the dimensions of this are, I'm just going to use a little dot to indicate that it's not really equal, but I'm just talking about dimensions. The dimensions of this are just 1 over time. If we think about units now, SI units, then the SI units for, well, of course, I need to combine these two things now and derive the dimensions of this guy. So I put those two together and I get the dimensions of viscosity are, I take this to the other side and I have force, time, and length squared, right? In SI units, I'm going to write this on red here, They are Newton seconds divided by meters squared. We will review the units in a little bit as well, the units of the SI system, just in case. So let's introduce the kinematic viscosity. The kinematic viscosity is simply the ratio of viscosity to density. So we write the Greek letter nu, and it's equal to mu divided by rho. So the dimensions of this are, I'll just write this down, are length squared times to the minus 1. And if we want to derive it, well, we already derived the dimensions of mu, and they are here, force time length to the minus 2. And let's write it in terms of mass. So force equals mass times acceleration, right? So it's mass times acceleration, which is length divided by time squared. So let me put the time to the minus 2 here. And we still have this term here, which is time and length to the minus 2, right? Follow so far? So we can write this as, now we can cancel some things over there, and we get mass, length to the minus 1, these two here, length to the minus 1, and time to the minus 1. Of course, we know what the dimensions of density are, mass divided by volume. So now we can find mass, length to the minus 1, t to the minus 1, and divided by density. So mass to the minus 1 and length to the 3. Right? Because this, if it was density, would be mass times length to the minus 3, but it's in the denominator, so we change all the exponents, the sign of the exponents. So here now we can cancel out the mass and so on, and you see that we're only left with length square. Here's a minus 1 with a 3. So we get length square and time to the minus 1. The SI units meters squares per second. Okay? So this is a good time to have a little bit of a break. What I'm going to do is I'm going to do the classes on a 40 to 45 minutes. Have a 10-minute break, and then have another perhaps 50 minutes and so, or plus or minus 5 minutes, depending on how it goes, so that you have time to text, do Facebook, Twitter, email, all of that in those 10 minutes. But in exchange, I will ask you to refrain from Twitter and Facebook during class. And I think that's a fair deal, because you only have to survive for 45 minutes without it. So you can also go to the bathroom or other things that you might need. Okay, so let's take a little bit of a break.